Now coming to memory. So memory, as I said, the bit is a basic unit, which is it takes 0 and 1, two values, 0 or 1. This is classical computer. Quantum computer has more memories. I mean, one unit of quantum computer has not 2 but many more. It can say more numbers. Now 1 byte is 8 bits, and a typical PC has like my laptop has 16 GB RAM. Okay, so 8 GB is typical. Now servers go up to 4 terabytes of RAM. I mean, of course, this will be expensive, so you need to put a lot of money for buying this much RAM. Now, so this is the right now. Memory is also told what technology, what kind of memory is that. So DDR4 is a standard now. I mean, your machine will be DDR4. I believe the new ones. So it's called double data rate. Don't worry too much about it right now. But this is important. How much data can be transferred from memory to CPU? Now, right, that's what we want. I mean, your arrays or like the vectorspheric data is sitting on RAM, and I want to process it. I have to send it to GPU, to CPU or GPU. So it can send the maximum. The peak speed is 25.6 gigabytes. Now remember, that guy can do 2.5 teraflops. Now tera is 2.5 times 10 power 12. Now here I have something like 100, well, more than 100 times less, because by the way, 1 byte does not contain one data. So one real number normally takes 8 bytes. So if I just divide by 8, then I'm stuck with how many numbers can it transfer. So it can transfer only 3 giga numbers. In the best possible scenario, 3 giga numbers. But that guy says, well, I can do 2.5 tera operations. So I simply am not able to send that much data. And that is the bottleneck right now. Okay, that's the real challenge in supercomputing. The memory is slower, and what to do with that? That's the problem. So you also need to know a little bit about how much memory is required to save a character or integer. So I have written this table for C language. Python also is very similar, but but this is standard. But there's one minor difference, but I'll tell you right now. So character typically requires 1 byte, like character A. Okay, it requires 1 byte. I mean, not A does not require 1 byte. A is a number, but all the keyboard characters. I mean, there's something like 50 of them sitting here on my. So plus some special characters. Okay, all that put together is 256 various combinations, and 1 byte is enough, right? 1 byte is 8 bits, so 2 to the power 8 is 256, right? 2 to the power 8 is 256, and I can store 256 characters in 1 byte. It turns out now we have a lot of characters for different languages, so 1 byte is not enough. So now people use 4 bytes to store all possible characters of different languages. Integer 4 bytes, and the range of integer will be minus 2 to the power 31 to 2 to the 31 minus 1. Okay. Now this you can figure it out. I mean, with 4 bytes I can maximize 2 to the power 31 and 2 to the power 32. But we have positive numbers and negative numbers, and of course there is a 0 sitting as well. So we divide all that numbers into this range. Now this is sometimes small number. I mean, 2 to the power 31 is basically 2 million. Now I may have a number bigger than that. Then I need 8 bytes. This is called C long, and the range becomes 2 to the power 63. Now sometimes that too is not enough. So in Python, it turns out if the number is bigger than this, it will allocate more bytes or more thing, but it will not truncate. I mean, it will simply keep putting more and more allocation of memory to store any size number you may need. Now Boolean normally will take 1 bit, but you see they store in 1 byte. So floating point, A floating point is real number. Okay, float. I'm going to tell you a little bit later. Why it is called float. So it's a very interesting idea, but you wait for maybe half an hour or so. I will come to float. So float requires 4 bytes, and the range of numbers is here. Okay, it can put 10 power 38 max, nothing more than that, and the smallest number is 10 power minus 38. Now, if I need a number bigger than this, then I can use 8 bytes, and that's called double. Okay, so this is called double precision. Okay, and this is called single precision. So is how many bytes are used to store a number, and double precision I can go to 10 power 308, and also how many significant digits, 15 digits for double precision and 7 digits for single precision. So my number in this is in decimal, not binary, decimal numbers. I can store only 15 significant digits, which is good enough for most applications. But suppose I want compute pi up to 1000 digits, then of course this is not good enough. So you need to write the program in more precise, advanced program to generate pi up to like 1 billion digits. Now estimates. So typical desktop has 4 gigabytes of 8 gigabytes of RAM or laptop. Now, what is the matrix size we can store in this RAM? Okay. Now you can compute. You can estimate what is the biggest size. I will not do it right now, but I'll just show you whether this matrix will fit inside the machine or not. So if n is 1000, so what is this number of bytes I need? So how many elements are there in this matrix? 10 cube squared, right? Because it's a matrix is 2-dimensional. So 1 million, 10 power 6 numbers. Now how much each number require is a real number. So double precision will 8. So I need 8 times 10 power 6 bytes for double. If I want single precision, then 4 times 10 power 6 bytes. Okay, for float. So I need this. Now it is smaller than this, right? This 8 gigabytes, and I have 8 megabytes, right? This is 8 megabytes. So this can definitely fit inside this laptop or desktop. But if I make it, let's say 10 power 5, 100,000, n is 100,000, then that becomes, it won't fit here, right? Because 10 power 5 squared will be 10 power 10 and multiply by 8. So that will be 80 gigabytes. And that's not, that can't be fit in this machine. Another, very big computer is, very big requirement is 4096 cube. We simulated one problem with this many grid points, and that requires, you can just do this operation, multiply and so on. It requires 1/4 terabytes. Okay, so it won't fit in, of course, in a laptop. It also won't fit in a standard a supercomputer. You need a very big supercomputer for this operation. Okay, so we had access to a big machine and we could do this operation. So as I said, there's a desktop, and of course there are slightly faster machines than desktops. It's called servers, and even faster is called super high performance computing clusters. Okay, these like supercomputers. Okay, this you can think of as supercomputers, but the name is not supercomputers these days. It's called HPC. Okay. Now these are many machines connected together. You can just imagine that many desktops are connected together. Of course, you don't put the desktops like boxes there because that will take too much space. There are pretty tiny nodes which are stacked in racks. Okay, I don't have a picture here, but you can just do Google and you'll find how do they look. Okay, now so basically there are lots of desktop nodes. Okay, so this is called node. They are connected together by a switch, and they talk via that switch. Now, I just mentioned 2 topmost HPC systems in the world. So the first one is Fugaku. This is the topmost machine in the world right now. It's in Japan. It has how many cores? It has 7 million cores. Compared to 64 cores of a ROM processor. Okay, it really, I mean, is astounding how many machines have been connected together, and it can do up to multiplied by 10 power 12. Okay, so teraflops. If you look at the numbers, it's basically 0.44 hexaflop floating point operation. It can do 0.4 times 10 power 18 operations per second. Okay, so it is basically, if you say hexa is 1, so we are half to that ideal machine which you are looking at. Okay, so we are not reached hexa scale yet, but we are close to it. Now there's difference between R max and R peak. You don't need to worry about it in this course, but yeah, so this is the power of this machine, and it takes around 30 megawatts of power. So it's like huge. Okay, 30 megawatts is more than a power requirement of full IIT. Now Summit is the second machine, is in US, and it has 2 million or 2.4 million cores, and it's basically 0.14 exaflop. Okay. Now anyway, this is just for your information. We are not going to program HPC system in this course. So Fugaku has some more details. I think I can skip this one. As I said, it has basically millions of cores, and this is a node, and each, so CPU of Fugaku is not a ROM processor. It's their own indigenous CPU, and that has 48 plus 4. I mean, there are 52 cores in a single node. And memory is also faster. It's not DDR. It's called HBM. So high bandwidth memory. Okay. Now, so we can read more about these machines in the internet, but like these are really fast machines.